Hello students! Today we are going to cover Chapter 1 of Form 5 Physics, Waves. So what is a wave? A wave is a disturbance which carries energy from one location to another without the transfer of matter. Waves are formed by a series of oscillations. Amplitude is the maximum distance of an object from its equilibrium position. The SI unit for amplitude is meters. The greater the amplitude, the greater the mechanical energy possessed by the oscillating system. Period is defined as the time required for one complete oscillation or vibration. An equilibrium position is a point where an oscillating object experiences zero resultant forces. A complete oscillation occurs when the vibrating object moves to and from its original position and moves in the same direction as its original motion. Frequency F is the number of oscillations that take place in 1 second. The SI unit for frequency is Hertz. F is equal to 1 over T, where F is frequency and T is period. In a force oscillation, if the frequency of the external force is equal to the natural frequency of the system will oscillate with maximum amplitude, and this is called resonance. An opera singer can break a wine glass with her voice due to the effect of resonance. Tacoma Narrow Bridge in the USA collapsed in 1940 due to the effect of resonance. The characteristics of resonance can be demonstrated with the Barton pendulum system. When pendulum X oscillates, the other pendulums are forced to oscillate as well. Pendulum D will oscillate with the largest amplitude. Resonance is used to tune your radio or TV to your favorite channels. Waves is important in designing alarms that prevent bridge collapse due to resonance. Let's look at the two types of waves, transverse waves and longitudinal waves. In transverse waves, the direction of vibration is perpendicular to the direction of motion of the wave. Examples include radio waves, water waves, ultraviolet, and infrared waves. In longitudinal waves, the direction of vibration is parallel to the direction of motion. Examples will include sound waves. Mechanical waves are waves that require a medium. Examples include water waves and sound waves. Sound waves can travel through air, water, solids, but it cannot travel through a vacuum. Electromagnetic waves. These waves can travel through a vacuum. They travel through electrical and magnetic fields that are generated by charged particles. Examples would include light, microwaves, radio waves, and X-rays. In Figure 1.4, the crest is the highest point on a wave. The throat is the lowest point on a wave. The amplitude is the maximum displacement of the wave from its equilibrium position. The wavelength is the distance between two successive crests or throws. Period T is the time taken for the wave to complete one oscillation. The frequency F is the number of oscillations in 1 second. Let's look at the relationship between speed, wavelength, and frequency. We know that speed is equal to distance over time, or wavelength over time. Since frequency is 1 over t, we can say that the speed is equal to frequency times lambda. So given that the frequency is 15 Hz and the wavelength is 3 centimeters, what is the speed of the wave? Using the definition stated before, where v is equal to frequency times lambda, we can solve it easily by multiplying 15 Hz times 3 centimeters, which is 45 centimeters per second. Question 2. A transverse wave is found to have a displacement of 4 centimeters from a throat to a crest, a frequency of 12 Hz, and a distance of 5 centimeters from a crest to the nearest throat. Determine the amplitude, period, wavelength, and speed of such a wave. Given the definitions from before, we can solve that the amplitude is 4/2, which is 2 centimeters, the wavelength is 5 times 2, which is 10 centimeters, and that the speed is equal to the frequency, which is 12 hertz, multiplied by the 10 centimeters, which is the wavelength, to get 120 centimeters per second. Reflection. Reflection occurs when an incident wave hits a reflector and is reflected back. The direction of the propagation of the wave is changed when it is reflected. The wavelength, frequency, and speed of the wave remains unchanged. The amplitude of the wave, however, may or may not change depending on the material of the reflector and the shape of the wave front. Reflection. The characteristics of reflection of light enables us to see objects. Objects that do not emit light are not seen in the dark. An object can only be seen if an incident light is reflected back to our eyes when interacting with an object. What are some applications of reflection of light? We have headlamps of a car, cat eye reflectors, end-scope in medication, telecommunications, which include optical fibers, periscope in submarines, and side and rear view mirrors of a car. Reflections of sound waves. The angle of incidence, I, is equal to the angle of reflection, R. Sound waves obey the law of reflection, that is, the angle of incidence is equal to the angle of reflection. The graph below summarizes the characteristics of before and after reflection of light. Refraction of waves. Refraction is the change of direction of a wave when it travels from one medium to another. This is because the speed of the wave changes when passing through a medium to another. In figure 1.17, the wavelength of the water wave in the deep area is longer than the wavelengths of the wave in the shallow water. Using the equation V is equal to F times lambda, we can define the different characteristics and the comparison before and after a wave travels from the deep to shallow or shallow to deep. Drawing refracted waves. When water waves travel from the deep area to a shallow area, it will be reflected towards the normal line. Water waves refract away from the normal line when traveling from a shallow area to a deep area. This lesson will be continued in part 2. Thank you for listening!